Hello everyone, welcome to my video. In this video, we will talk about example 3/200. It is part of section 3.13, impact and coefficient of restitution. After reading the question, we want to determine the coefficient of restitution E for a steel bar dropped from rest from here at certain height h above a heavy horizontal steel plate. Okay, what does this mean? It means this plate is, you can consider this as a ground, a solid surface. It won't change. If the height of the second rebound is h2. Second rebound is h2. So when we drop it, we'll touch it, bounce back, and touch, bounce back. So this is the first rebound. This is the second rebound. The second rebound will given the height is h2. So you need to connect from the height h to h2 and trying to find the coefficient of restitution. To start, let's write down the equation for coefficient of restitution first. E equals to V2 prime minus V1 prime, V1 minus V2. Okay, remember, these are absolute values, so it doesn't really matter which one goes which. But now, looking at this equation here, the coefficient of restitution is not depending on h. It's depending on the separation velocity and approaching velocity. What we did in class is we have two bars. When the two bars collide with each other, they will separate. However, now thinking about this is the wall is not going to move. And when the bar collide the wall, or in this case, when the bar collide with the plate, like this, the velocity of this ground or of this surface or of this steel plate is always zero, right? That means the V2 prime and V2 will always be zero in this case. The only velocity that is going to matter in this case is the velocity of the ball approaching to the plate, and when it's bounced back, the velocity of the ball leaving the plate, because the velocity of the plate is always zero. Okay? So, that means we want the velocity of the ball. How can we get the velocity of the ball? We were given the height. Yeah, I hope you can think of, we need the energy equation. The potential energy converts to kinetic energy when from mgh to 1/2 mv squared. But before that, let's separate these two bounces, so we are very clear about which velocity is which. Let me do this very slowly here. So we have a surface, horizontal surface, and the ball is going to be dropped. I'll use a different. So the ball is going to be dropped. And this first height is dropping by h. And when the ball approaching the ground for the first time, you have velocity v1. And then when the ball touch the ground, the ball will go back, right, to a certain height. So let's say the ball go back to somewhere here. Go back to here, and we'll call this h1. And the velocity of the ball leaving the ground during the rebounds we'll call v1 prime. And this whole process is here, right? I'm just separating it. And this is our first impact. And then we will copy we'll copy the status of this ball here. We'll copy it. Copy and paste. We'll copy it to here. Now this ball is going to drop, going down again, right? And the same height h1, but now the ball is going down. So the ball will coming down again with another velocity, approaching to the ground. We'll call this v1 prime. If you recall from the projectile motion, from the same height, no friction, no air drag, the same height, whatever the launching velocity is, you'll get the same velocity at the same point. So that's why we have v1 prime and v1 prime, but the direction is different. One is launching velocity up, one is coming back velocity, v1 prime. And in this case, the v1 prime is the approaching velocity for the second impact. The ball is coming back to the ground, and then the ball will bounce back. Okay, another bounce back, the second bounce. That's what we are interested in. So the ball will bounce back to another height. Say somewhere here. I want to make it the same, approximately the same size. Okay, and we'll call this H2. Okay, these are the given condition, H and H2. And there is a middle parameter, H1 and V1 prime here. And in a moment, you'll see how are we connecting them together. And this is a second impact. Okay, that's our second impact. Now, from the energy conservation perspective, we can calculate the velocity of V1 and V2 and V1 prime, right? Because from an energy perspective, the only thing that changing between each other in terms of energy is potential energy converts to kinetic, and kinetic energy converts to height. Okay, that's the only two difference. The two things are changing between each other. So from the energy perspective, we'll do energy conservation. Okay, we'll do this one at a time. For the first impact, which is this one. Okay, we'll have, naturally our datum will be this one. Okay, this will be our datum. It's the surface. So first impact will have mgh. The height converts to 1/2 mv1 square, which describes this scenario. And we'll rewrite it. v1 equals to square root 2gh. Okay, and our second impact, we'll take a look here. For our second impact, we'll look at this one directly. Okay, I forgot one more thing. For when the ball bounce back for the second impact, there will be a velocity. We'll call this v2. Now looking at this rebounds in the second impact, when the ball touched the ground and bounced back, what we have is we are converting that velocity in the second impact, we're converting that kinetic energy, 1/2 mv2 square, back to the potential energy H2 equals to mgh2. We'll write V2 on the left-hand side. So we'll get 2gh2. And this is describing this part. This is describing this part. Now, we have a intermediate state. Let's take a look. For the intermediate state, what do we have? Intermediate state, we have H1 converts to V1 prime. Or looking at this one, the same thing. V1 prime converts to H1. The potential energy converts to kinetic energy, and kinetic energy converts to potential energy. So we have mgh1 equals to 1/2 mv1 prime square. This is describing this part. So our v1 prime can be written as square root 2g h1. Okay, seems promising because all the velocities can be written as gravitational constant and height. And let's see if we can get rid of this h1 here, because h1 is not given. We're only given h and h2, so we need to eliminate h1, not erasing. Okay, eliminate h1. Okay, now comes to the mathematical operations. For the first two, the restitution of the coefficient of restitution, we'll do the calculation using the first impact and second impact. Because the coefficient of restitution will be the same throughout the entire bounce back, dropping and bounce back, dropping and bounce back scenario, because it's a steel ball and steel plate. The two materials remain the same. Same materials will have the same coefficient of restitution. So that means we can find the expression of coefficient of restitution between first impact, second impact, and second impact with intermediate state, or intermission in this case. Okay, so for the first one, we will have E equals to separation velocity over approaching velocity. So the separation velocity for the first one, what do we have? We have separation. V1 is leaving, but the ground always have a zero velocity. And the approaching velocity, we have V1 approaching the ground, but the ground has a zero velocity. So our coefficient of restitution will be written as V1 prime, the separation, over approaching. It doesn't matter because it's doesn't matter the order here because it's absolute value. And then for these two, we'll do the same thing. We'll calculate our restitution, a coefficient of restitution, the separation velocity over approaching velocity. These two together, we will have V1 prime over V1 equals to V2 over V1 prime. Or just write as v1 prime square equals to v1 v2. Okay, now you can choose any of either this one with this or this expression with this to eliminate the v1 prime. And you only end up with v1 and v2. And v1, v2 can be written as 2gh and 2gh2 under the square root. Okay, we'll use this one and this one. Okay, we'll rewrite it, put them together. Put them together here. We'll have E equals to square root v1, v2 over v1 equals to square root v2 over v1. Okay, and we're subbing v2 and v1 in terms of gravitational constant and height, as we got on the previous page, based on the energy conservation. So we'll keep going here. E equals to v2 is 2gh2 under the square root. v1 is 2gh under the square root. The whole thing, simplify it, we end up with h2 over h to the power of 1 over 4. This is our answer. Now, thinking back to the scenario, if the two materials remain the same and one material is fixed, the coefficient of restitution will determine how high the object can bounce back after the impact. It kind of makes sense because coefficient of restitution is exactly describing this scenario. It is describing how rigid the collision is. Okay, h2 over h to the power of 1 over 4 is our answer. This is all. Thank you for watching. I'll see you next time.